All right, so the question is about mirror images and chirality.
Yes.
So for a molecule, so a molecule can either be chiral or achiral, the same way that the alcohol can either have a pi bond or not have a pi bond, right? And so if it's chiral, that means that it has a carbon in it that has 4 different groups attached to it. If it's achiral, it either does not have 4 different groups attached to a carbon, or it's meso. Those are the 2 ways that you can have an achiral compound.
Maybe my better question is define meso for me again.
Meso. So a meso compound would be one that has a plane of symmetry in it. So for example, this was the example compound that we used originally to talk about meso. We could also have a compound that looked like this that would be meso. Right, so we can see that there's a plane of symmetry going through here and then also going through here. So if they have 2 or more chiral centers and they also have a plane of symmetry somewhere in them, that makes them meso. The upshot of them being meso is a meso compound doesn't have an enantiomer. So if you try to draw its enantiomer, you're just going to draw the original compound again. And because it doesn't have an enantiomer, it's not actually optically active. Which makes it achiral.
Achiral. So
Yeah.
meso are not optically active.
Right.
And if you try to draw the mirror image, if you try to draw their enantiomer, you just get the same thing.
Mm-hmm.
Because you would flip those.
So if I switched the dashes and wedges here, I would just have my chlorines like that. And then if I took this molecule and I flipped it over, if I flipped this over, I would still have this 5 guy. Now this one would be on this carbon, right?
Right.
And if it were going back and I flipped it over, then it would be still going back.
Could be what?
It would be a wedge, right? So it would be coming out. And then this one would be this guy now. And what would happen to that? It would be a wedge. So I attempted to draw the enantiomer, but in fact, I just drew a different conformation of the same molecule. So that's a factor in it being meso. Did you have a related question, Capriana? Okay.
Yeah, going off like after reactions.
Mm-hmm.
3 on the practice exam. I don't understand.
Number 3 on the, right, but the multiple choice or the short answer?
Oh, I'm sorry.
No problem. The multiple choice. Yeah, that's because 3 doesn't have a correct answer. So when I posted the practice exam, I think I put that underneath it on Blackboard. So number 3 does not have a correct answer. I thought it was D when I wrote the exam, but no, it is not. D is not optically active. More questions about optical activity and chirality as long as we're on that, Nicole.
Can you give us an example of an achiral molecule that is not meso?
An achiral molecule that's not meso. So then we might have, say, that. So it has 2 of the same groups attached to it, so it doesn't have a chiral center. So that carbon is not a chiral center, and that would make that compound not a chiral compound, so it would be achiral. Or if we had, say, something like that, I could even draw in dashes and wedges, but it doesn't make any difference, right? This still has 2 of the same groups on it, and so if it has 2 of the same groups on it, that's not going to be a chiral center that it's attached to.
Are there any achiral molecules that have
4 different groups have a chiral center?
But is not meso?
No.
Okay, thank you.
Yeah, so there are no molecules that have a chiral center, are achiral, and are not meso, right? So anytime that we have a molecule that has a chiral center but is achiral, it will be meso. Zoe?
So, meso, they have to be achiral, right?
The molecule is achiral,
Oh, but they can have.
but they can have chiral centers. So this is a chiral center, this guy right here, and this guy also is a chiral center. But the molecule is achiral.
Okay.
So what would happen if I took that molecule and I put it in a polarimeter to measure the rotation, the optical rotation? What would it be? What would I get? 0. Exactly. So no optical rotation if it's meso, which is another way of saying that it's achiral. So if it's achiral, it will have an optical rotation of 0. It would be optically inactive. Other questions about stereochemistry stuff? As long as we're on this topic, we might as well stick with it. So the question is, what's the difference between heterolytic and homolytic? Come on, move. So the difference between heterolytic and homolytic is that heterolytic cleavage would be like loss of a leaving group, for example. So here, we get 2 ions. And a homolytic cleavage is something that happens to some molecules. And instead of getting 2 ions out, what we get are 2 radicals. So in a homolytic cleavage, what we do is we split that bond down the middle, and each of the atoms that were connected get one of those electrons. So this is homolytic. And the one up above is heterolytic. So this heterolytic cleavage will always give us 2 ions, and the bond will be split unevenly. Those 2 electrons from the bond will go on to one of the atoms involved in the bond. Whereas in a homolytic cleavage, we kind of break that bond in half, and each one gets 1 electron. More questions? So the question is about how we identify primary, secondary, and tertiary, and unfortunately, really the only way, like once you've had enough practice at it, you can just kind of glance at them, and you don't have to like count them up anymore. But really what you have to do is look at your alkyl halide. So this would be our alkyl halide, right? Find the carbon that the halogen is connected to, and then count how many carbons, 1, 2, that carbon is connected to. So this would be secondary. Yeah? Sure. So the question is to go through number 4 on the short answer. So the NMR question? Perfect. All right, we'll just start a new page here. All right, so for this one, we have, I'm just going to rewrite it here for the folks following along at home. We have 7.23, 7.09, 5.17, 4.9H, huh? And then we have our IR and our formula. And for the IR, we have a peak at 3430 inverse centimeters, and then another one at 1625 inverse centimeters. All right, so what is the first thing we should do when we have an NMR problem? HDI, right? So the HDI, the formula will be given to you. So 2 times the number of carbons, so 2 times 9, plus 2 minus 12. Remember that oxygen doesn't go into this formula at all. So that would make 18 plus 2 gives us 20, minus 12 is 8, so we have 4. So if we have an HDI of 4, what does that tell us? Yeah, so HDI greater than or equal to 4 will always mean an aromatic ring. And so we know that if we have exactly 4, we have an aromatic ring, and there's no other double bonds or triple bonds or rings present in our molecule, okay? So then let's go ahead and glance at the IR. So 3430 inverse centimeters, and then it mentions that it is broad and strong. So any idea what that might be? That's an alcohol. So we know we have an OH, and then 1625. Yeah, that's another sign that we have an aromatic. So that one's not that interesting. But the alcohol, that's a really good thing to know, because that accounts for our oxygen atom. And so now we know where our oxygen atom is, right? So that's kind of nice. All right, so now we can go through the set of shifts here and decide what they all are. So these two are both in that 7 to 8 region. So what do those correspond to? Yeah, so that's our aromatic ring again. Okay, so we know we have how many hydrogens on our aromatic ring? 4, right? So 2 here and 2 here. So those 4 are all in that general chemical shift range, and so those are going to come down to, there's going to be 4 hydrogens and then 2 R groups. So pretty much any time that we have 4 substituents on our benzene ring, on our aromatic ring, they're going to be in this pattern where the 2 R groups are directly across from each other. Just because that's essentially the only one that gives an identifiable coupling pattern. So you get a doublet and then another doublet for each of your sets of 2 peaks. All right, so we know what that is. What is this thing at 5.17 that's 1 hydrogen and a singlet? Yeah, that's the OH, exactly. How did you know that? How can you tell it's an OH? Yeah, so the shift is in the right region, so those are usually in the somewhere in the 3 to 5-ish range. And then we could also tell because it's a 1 hydrogen singlet, right? So alcohols will usually just be 1 hydrogen and they never couple, and so they'll always show up as a singlet in the spectrum. Good. So now we have those 2 groups figured out. Then here we have a 1 hydrogen quartet. So how many neighbors does that have? If we have a 1 hydrogen quartet, if we have a quartet, how many neighbors do we have? We have 3 neighbors, right? But I have 2 signals that each have 3 hydrogens. So how do I know which one is the neighbor? It has to be the doublet, right? I have to look when one thing couples one thing, when one thing couples another thing, that another thing also couples the first thing, right? Coupling always goes both ways. So if this is a 1 hydrogen quartet, we need to look for a 3 hydrogen doublet because it has a 1 hydrogen neighbor. So these 2 are going to be neighbors with each other. This one is a singlet. And so if we have a 3 hydrogen singlet, what kind of thing is that probably? That's going to be a methyl that's not bonded to anything, right? Or not bonded, it doesn't have any hydrogen neighbors, I should say. Okay, so sorry, I got distracted from my chemical shift thing here. So we have 4.98 for that 1 hydrogen quartet. What sort of thing is going on there in all likelihood? Yeah, so that must be the one that the oxygen is on, right? So we have a carbon that's bonded to a hydrogen, and that carbon must also be connected to an oxygen. That's where that very high chemical shift value comes from. And then this has 3 neighbors. And then there's other stuff going on there too. We also have RCH3, right? That's for this signal right here. There's something and then a methyl group. There's something with no hydrogens on it and then a methyl group. And so what we have is this piece here, and this piece here. And so if we have these 2 R groups here, they must correspond to these 2 R groups here. And so the answer is going to have a methyl group on one side and then this guy on the other side. Questions about how I got that? All right, I had a specific question to do a NMR problem, so do you guys want to do another one? Yeah. Okay, perfect. All right, folks at home, if you want to try it, this is another NMR problem. Go ahead and pause the video and give it a try. All right, so let's take a look at this. So I'm not going to go through calculating the HDI. I think you guys probably have that under control. So this has an HDI of 1. So what can we say, what's going on here? So what sort of, how, is this a methyl group, an ethyl group, a CH2, like what's going on here? It's got to be a methyl group, right? And based on the chemical shift, what can we say about it? It's got to be next to an oxygen, right? So I need an OCH3 with an R group here, right? So that has to be what's going on here in order to give that chemical shift of 4.3. There's no other possible functional groups that we could have that would be in that range. An alkene, which would be the other possibility, we would expect more, we would expect not to have 3 identical hydrogens on an alkene, right? That would be pretty surprising. 3 hydrogens or 6 hydrogens or 9 hydrogens is pretty much always going to be some group of methyl groups. And they certainly wouldn't be a singlet, they'd all be like coupled to each other. So it's not going to be an alkene, so that leaves us with an OCH3 as our option, which makes sense because we have a couple of oxygens in the molecule anyway. Could also be a halogen, but again, we don't have any halogens, so it can't be that. Okay, then we have a 2 hydrogen triplet, and how many neighbors does this have? Oh, sorry, first of all, 2.1, 1.4, and 0.9, what sort of functional group will this be? So these are all alkanes, right? Right, so we have 3 alkanes. This one is slightly out of the region, and so it might have something kind of nearby, but it's not anything too extreme. All right, so how this has a triplet, this is a triplet, so how many neighbors does it have? It has 2 neighbors, so which one has to be its neighbor? The sextet, right? So this is its neighbor, but if this is its neighbor, this is a sextet. How many neighbors does that have? 5. So we know that it has 2 neighbors here, so who else has to be its neighbors? It has to be this one, right? So there's another 3 hydrogen guy. So this is a triplet because it's coupled to these 2 hydrogens, and this is a triplet because it's also coupled to these 2 hydrogens, right? So what we actually have here is a propyl group. So we have a CH3, let me draw that again. Look, erasing, it's magical. So we have a CH3, and then a CH2, and then a CH2, and then an R group, right? So we have our CH3, that is this signal. We have our CH2, which is this signal. So that's coupled to 5 different hydrogens, which makes it a sextet. And then we also have this guy, which is coupled to these 2, so that would make it a triplet. So that is this guy. So we have taken care of all the hydrogens in our molecule. So at this point, we can actually go back and figure out what we still have left in our original structure. So how many carbons have I accounted for? I have 1, 2, 3, 4. So C4. How many hydrogens have I accounted for? How many hydrogens have I accounted for? Hopefully all of them, because I accounted for all those signals. H10. So all the hydrogens are done. And then how many oxygens have I accounted for? 1. So what's left? A carbon and an oxygen, and we also have an HDI that we haven't taken care of at this point, right? So it turns out that there's also going to be a carbonyl in this molecule, right? So we can kind of deduce that from the fact that we have a carbon and an oxygen and an HDI left over. Normally I probably would have given you like an IR or a C13 NMR or something that gives a strong signal for that carbonyl, so you wouldn't have to do it by process of elimination, but it is totally possible to do it by process of elimination as well. Like those are the things that are left over and I have to figure out how to put them together, okay? So now at this point, I have my pieces. I have this guy with 2 R groups on it. I have this guy with an R group on it and this guy with an R group on it. So now I just have to smush those guys together. And so I have my carbonyl. I have my OCH3. What? You can't see green? Okay, good to know. Oh, wow, that is terrible. All right. Looks fine on... Okay, so we have our carbonyl, we have our OCH3 attached to it, and then we also have our propyl group attached to it. So that's this guy is here. So the OCH3 we got from the original series of chemical shifts. I've moved the screen up so you can't see it anymore, but it's there, I promise. So the question is, how did I come up with a propyl group based on these 3 guys? Well, it's probably a little bit easier because, again, I did write this problem like 10 minutes ago. But if I were you, what I would do is I would say, okay, I have a 2 hydrogen triplet. So I need to have 2 guys, I need to have 2 hydrogens next to this signal. So where can I find 2 hydrogens that are next to this signal here? Okay, so what I could do is I could write, I know, so this is these guys here. Okay, so I can write down, I know I have a CH2, and I know that there's a CH2 next to it because that's the only way that I can get a triplet, right? So now I look for that CH2. Well, there's only one other signal in here that's a 2-hydrogen signal. Okay? So I have a 2-hydrogen signal. That one is a sextet. So because that's a sextet, that tells me that I must have 5 neighbors. I've already drawn in 2 neighbors, and so then I need to add 3 more. And then I find that those 3 are this guy, which is our 3-hydrogen triplet. It's a triplet because it's also connected to those guys. So an R group is just a generic something. Like I know there has to be something there to give this carbon 4 bonds, right? And I know it's not a hydrogen, right? But I know I know there's something there, so it's like a placeholder. And then I can use that as a way to connect the molecule together. Another thing that people do sometimes is they'll like write a squiggle like that. Like I know there's a bond to something, but I don't know what it is.
So you took like the R from like the 2 things.
So I had, 3 different pieces that had R groups on them. I had the carbonyl that had 2 R groups. So I need to replace both of these R groups with something. And then I also have this piece that has an R group. So I'm kind of combining these 2 R groups into one. So I'm putting this guy over here. And then I also had an R group way up at the top here. Oops, this guy. And so I could use that one on the other side of the carbonyl. But again, if you can come up with the pieces, that'll get you most of the points, right? So don't spend an enormous amount of time trying to put together the molecule because you only have 50 minutes, right? Just a piece of advice. Yeah, David.
How did you know it was the carbon and the 4 hydrogen bonding and oxygen? The first one, how did you figure that out?
It's because, so the question is, how did I know that this was a methyl group next to an oxygen? Is that the question? It's because of the chemical shift. So it's at 4.3. So if I look at my options for things that might be at 4.3, right, I can get out my chemical shift table. And the things that make sense there would either be an OH, which I could possibly have, but that wouldn't be 3 hydrogens, right? So I can kind of rule that one out as a possibility. I could have an alkene, but again, it doesn't make sense to have 3 identical hydrogens on an alkene, right? I would get more than one signal there based on the 2 different carbons of the alkene would give me at least 2 different signals, and so it can't be an alkene. And so by process of elimination, then I end up with something where I have a hydrogen and then something electronegative. So this could be an oxygen or it could be a halogen. But somehow I have to have 3 identical hydrogens. And again, whenever I have 3 identical hydrogens, I can just jump to the conclusion that they're a methyl group because they'll always be a methyl group. And then that's bonded to a carbon that's bonded to some sort of heteroatom, some sort of electronegative atom, so an oxygen or a halogen. Does that make sense?
Yeah.
Perfect.
So would it have a much lower like signaling if it was like if the methyl group was directly bonded to the C that was directly bonded to like the O?
Exactly. So if the molecule were like that instead, if it were missing that second oxygen, then this would probably be around 2. All right, so the next question is about number 10 on the multiple choice of the practice exam. So we have 4 options here, and the question is, which one will react most rapidly? Is this the one you wanted?
Yeah.
Yeah. Which one will react most rapidly in an SN2 reaction? So an SN2 reaction prefers small substrates. So it wants methyl or primary if possible. It will accept a secondary if pressed. Tertiary SN2 reactions just don't happen at all. And if we have an sp2 hybridized carbon, we also can't do an SN2 reaction. Turns out you also can't do an SN1 reaction there either because their carbocations are super unstable. Anyway, which of these can I rule out as saying they don't do SN2 reactions at all? Yeah, so no SN2 because this is sp2 hybridized. What else? the second one, so no SN2 because it's tertiary, right? So this carbon that the chlorine is bonded to 3 additional carbon atoms, so that makes it a tertiary alkyl halide. So no SN2 there. What about this one? Primary, secondary, tertiary? Sorry, I forgot. You can't see my hand. This one. Woo. Sorry. Is it what? No, I was just playing with my pointer. Yeah, it's secondary. Nope, I was just being silly. And then what about this guy? Woo. Sorry. Yeah, that's going to be primary. So which one's going to be fastest? It'll be the primary. Yeah, Capriana.
So it's not like based on the chlorine itself, it's based on like the carbon of the chlorine.
Exactly. So it's not really based on the chlorine itself. It's based on the carbon that the chlorine is attached to. So that's where we get that primary, secondary, tertiary designation. That's exactly right.
If the question number 10 asks which would react most rapidly in an SN1,
Ooh, excellent question. So which one would react most rapidly in an SN1 reaction, do you think? It would be B. So fastest in an SN1 reaction, again, because it's tertiary. So SN1 reactions also don't happen on sp2 hybridized carbons. And they also wouldn't happen here. We can't get it on a primary substrate either. Oops, sorry. No SN1 because it's primary, and primary carbocations are so unstable that they basically don't exist. You can't make them. Yeah, Nathan. So you can't have an SN1 or an SN2 on sp2 hybridized carbons. They only happen on sp3 hybridized carbons. The reason for SN1 orbitals or SN1 reactions is because those carbocations are super unstable. You can't, a vinyl carbocation where it's like this, the plus charge is actually on that double bond, like attached directly to the double bond, those are super unstable. So the question was about the first short answer question, and especially part D. So I'm just going to draw part of that penicillin ring system. All right, so the hard part here is assigning priority. So for this one, we have to think about the hands again, right? So here is our chiral center. So what is the hand of this carbon right here? The bottom one. Ooh. Yeah. So that'll be OOO, right? But actually before I get to that point, I want to ask myself, what atoms is this carbon directly connected to? So it's attached to a carbon, a nitrogen, and another carbon. So of those three, which one is going to win? The nitrogen, right? Oops, plus charge, that's not right. So this is a 1, right? So then the debate is between and this guy up here. So what is this guy's hand? SCC. And I'm writing the sulfur first on purpose. You always play your best card first, okay? And then it basically comes down to you keep going through the cards from best to worst, and as soon as you find a tiebreaker, then that's the one that's going to win. So the sulfur will win. It has nothing to do, and I stop before I even get to the carbons and comparing it to the oxygen. I'm just comparing sulfur and oxygen. Sulfur wins, therefore this one would be 2, and down here would be 3, and of course our hydrogen is 4th, and I'm not going to go through the rest of how to, because I think the priority is the tricky part here.
So
Yeah.
wouldn't we switch it and it would be an S?
So yeah, it should be S, which is,
It's R and the P, I think. Oh, did it?
yeah, I don't think it was ever up as R though.
Yeah, it was like R and D cross out.
I did indeed, that is what happened, yes.
Okay. Got it.
Yep, so there should be like a black X through the R and then a like squiggly S written nearby in some random color that I could get whatever my PDF program to write in. So the question is, how do we know what leaving group is a good leaving group? So essentially, we're looking for something that's going to be stable, okay? And so that means not reactive. So that means things like, so let's say that you took this and you spilled it on yourself. Would you be okay or not? All right? So let's see here. Let's say that we had, so the kind of the classic example is going to be a chlorine, right? And I'm going to make this tertiary so I can pretend we're doing an SN1 reaction. All right, so now the chlorine leaves. So now we have a plus charge here and a Cl minus. So do we ever encounter Cl minus in our daily lives? Have you ever dissolved sodium chloride in water? Yeah. Were you okay afterwards?
Yeah.
Yeah, you were probably fine. Yeah, unless you got high blood pressure. So the Cl minus is something that's really stable, right? And so that's what we want to look for. We want to look for things that are produced that are really stable, okay? Another example might be this. So if this were to leave, we would get that same carbocation and then OH minus. So that would be like a hydroxide solution, right? What would happen if you took a hydroxide solution and you spilled it on yourself? You would get a burn, right? Right? I mean, it depends on the strength of the sodium hydroxide, but nonetheless, we know that hydroxide is fairly reactive as far as these things go. It's certainly more, like what would you rather drink? A sodium chloride solution or a sodium hydroxide solution, right?
Yeah.
Right? So this one is fine, this one not so good, right? So it's reactive, it's unstable. It's not something that's like, I'm just gonna go out on my own and be fine with that. It really wants to react with some H+, right? So if it's looking for something to react with, then it's going to be unstable. It's gonna be a bad leaving group. It's not just gonna take off from the molecule and be like, see you later, bye, right? So let's contrast that with, this is supposed to be the same molecule. So if this leaves, it came out kind of sloppy, but whatever. You guys know what I'm talking about. So what would be the leaving group here? H2O. I don't know if you guys have ever heard of this. It's a chemical called water. I actually brought a sample of it. Sorry. I'll pass it around. Everyone can take a look. Right? So this is going to be a good leaving group because once it's gone, it's very stable. Okay? This is going to be a bad leaving group, so this reaction isn't going to happen because this is very, very unstable, or moderately unstable. There are worse things. You can get OH to leave under like really extreme circumstances, but not in SN1 and SN2 circumstances. Chlorine is going to be a good leaving group. Bromine or iodine, again, those are the conjugate bases of strong acids, right? And so they're going to be very weak bases, so they're going to be, you know, even less reactive than that Cl minus, okay? So if you spilled sodium bromide or sodium iodide on yourself, you would also be totally fine.
So that reaction won't happen, you said? Like,
That's correct. This reaction will not happen because that OH is a bad leaving group.
what does
But
this say?
again, like we haven't gone into detail on this leaving group stuff yet, so don't worry too much about it, okay?
What about the stability of the carbocation? What is that? Because I know that's a good question. One of the multiple choice questions is which carbocation is most stable. So what? And I know how to. Well, I think I know how to tell the stability between those, like looking for resonance and all that stuff.
Right.
But what does that tell us about the reaction?
So I used the same carbocation in each case, and they're all tertiary. So the carbocation isn't going to be the problem in this reaction. It's going to be the leaving group that we're going to have to think about.
When would it be?
When would it be a problem? So
Yeah.
if, let's say that I used, so the question is, when might the carbocation be a problem with the reaction? Let's say that I used something like this. Well, that's never going to leave, right? Because it would make a primary, oops, I put too many carbons there. That would make a primary carbocation, which is very, very unstable. So we need to have secondary or better in order to move forward with the reaction.
Thanks.
Yep. Hannah, did you still have a question?
No, I think
Okay. Yeah, so the very last question on the practice exam was based on a ridiculous story that I told my class last year about some ill-tempered weasels and a nuclear-powered dryer. And I'm sorry I didn't share it with you. If you want, I'll tell it to you sometime. It's not a true story. So that was basically like kind of just an extra point for like, did you come to class? And also to, you know, lighten the stress of the exam a little bit. So the question is about number 5A from the practice exam. So we have this as our product plus BR minus. And then you were asked, or the exam asked to determine the nucleophile as well as the electrophile. So how did we know? So the first question I want to ask you is this an SN1 or an SN2 reaction, and how can we tell? So look at the stereochemistry of the products. What do we expect for the stereochemistry of an SN1 reaction? Would we get a single enantiomer? No, we would get a mixture of two enantiomers. So we can determine that this must have been an SN2 reaction because it only has a single enantiomer as the product. We can work backwards from that to figure out the stereochemistry of the starting material. So the nucleophile is the easier part here. That's just going to be SH minus, right? And then the original electrophile or substrate had its methyl group coming out, right? I didn't do anything to that center, and so nothing is going to happen to that one, but the bromine should be going back. And the reason that it should be going back is because in an SN2 reaction, right, we have to attack that antibonding orbital, which flips the stereochemistry of the atom that the reaction is taking place at. So it's that umbrella thing, right? So it has to, this is the backside attack. And so we must have started with this. Uh-oh, my pen died. So we must have started with, oh, sorry, I need to plug it in for a second. Uh-oh. So the bromine here is going to be the leaving group, right? So that was on the molecule at the beginning, and then the mechanism would be this guy attacking and that guy leaving. Too much going on there. So we would have this guy attacking that carbon atom and the bromine leaving to get us to the product. Again, it doesn't ask for a mechanism, so you don't have to draw one, but that's what it would look like. So backside attack, that's only SN2. Yep.
Just the same direction, but flipped from dash to wedge.
Correct.
How did you know it was a backside attack?
Because it's SN2, and it has to be SN2 because you only get one stereo isomer as your product. An SN1 reaction would give you two. Hannah?
So then how did you know for C that you were going to give two answers for the product? Like, how are you supposed to know the difference between SN1 and SN2 if you don't know the product? Like, you're just supposed to assume the
In part B of 5, yeah, so that's something that we just haven't talked about yet. So we'll get to that on Thursday or something like that. So questions like 5B will not be on the exam. Now, if that had been tertiary instead, then I would have expected you to know. So if we had something like this, and then like an ethyl group coming off or something, then I would expect you to know that it's SN1 and not SN2. But secondary are tricky because either one can take place. It turns out that this one has a weak nucleophile, which favors SN1 over SN2, but you don't have to know that, so erase that fact from your memory if necessary. 5B is not on the exam.
What about like question 6?
Question
Are we supposed to know
6.
that's going to be SN1 because it's tertiary and the product is also.
You know that it's SN1 because it had to undergo a rearrangement.
And why did it have to undergo a rearrangement?
Well, you can see what, this is again one of those cases where you can see what the product is. So if we draw the carbon skeleton originally, and then we draw the product, right? So let's try, if we did an SN1 reaction, we couldn't get to that product, right? So if we had Cl minus and it attacked here and the bromine left, well then our product would be that. Is that what we got? No. And so we can say it cannot have been an SN2 reaction. It must have been SN1 because it went through a carbocation rearrangement.
Okay, so you would give us something like that. You would just
So
explain
whenever I ask you for a mechanism, I will always give you the starting material and the product. Yep. So I think predicting the product and doing the mechanism are two different questions, and I don't like to combine them personally. Yep. Logan?
For a mechanism on an SN2 reaction.
I could certainly ask for a mechanism on an SN2 reaction.
Right?
Only if I explicitly ask for it. So in general, the SN2 mechanism would be just this, just those two arrows happening simultaneously. Yeah.
The compound above the one you just circled,
This one?
yes.
Okay.
How do you know that that one is SN1?
So it's because it's tertiary. So tertiary substrates always favor SN1. SN2 reactions can't happen because we can't get to the antibonding orbital. Right, so this is our sigma star. There's just too much stuff there to be for the nucleophile to be able to access that antibonding orbital.
So if you talk about SN1 and you have a carbocation and rearrange, we just always do that we should.
Oh, right. I guess we only have this room until 6. I forgot about that. All right.